So we wrote the Hamiltonian for the n-body system. Let's go back to the three-body. Let's do some simplifications here that will enable us to solve the problem, at least in some configurations. At first, let's go back to this figure and remove the origin, since we are using coordinates where the origin is in the primary. And we only have three bodies here, so let's eliminate the n3. And now let's do the approximation that the mass of the third body, m2, is equal to 0. Then under these approximations, the potential for the body 1 then becomes minus g m0 plus m1 over r1. And the second term, the summation, cancels out because you are excluding j equal to 1, and the second body doesn't have mass. So the body 1 indeed only moved under the influence of a two-body motion. As for the body 2, then it becomes gm0 over r2, and the summation, you're excluding j equal to 2, but that doesn't matter because the body itself, m2, does not have mass. So we would cancel out. For j equal to 1, then you have, so indeed this is the attraction from the sun, the attraction from the planet, and the indirect term. We'll have that the body m1 then is going around in its orbit, in its Keplerian orbit. The body 2 has its orbit around the sun and a perturbation. The Hamiltonian for the second body, therefore, is the Keplerian Hamiltonian, the kinetic energy plus the potential of the sun. So this is the energy of the two-body motion. Let's write that in terms of the semi-major axis and the perturbation. The problem now becomes how to write the perturbation in terms that it yields insight on the motion. Let's first remove the subscript 2 from the radius vector, since this is the radius vector that we want to calculate. And the modulus of R1 and R can be calculated by the law of cosines. If we have the angle between them being psi, this is the vector R1 minus R. Its modulus then is given by the law of cosines, going to be r1 squared plus r squared minus 2r r1 cosine of psi, well, the square of this. So if you take the square root of this, invert. Now you will identify this as a generating function for the Legendre polynomials. This is almost identical to what we have, except that the generating function of the Legendre polynomials has a 1 in the denominator. So let's extract r1 from the square root. And therefore, this becomes square root of 1 minus 2r over r1 cosine phi plus r over r1 squared. Now, this is identical to the generating function of the Legendre polynomials. If t is equal to r over r1 and x is equal to cosine psi. So we can write the inverse of the modulus then as a summation of Legendre polynomials in cosine of psi. Now, if we put this definition back into the perturbation Hamiltonian, we can simplify this a little further if we write the dot product of R and R1 in terms of their modulus times the cosine of psi, since psi is the angle between R and R1, and identify cosine of psi as the first Legendre polynomial. The zeroth Legendre polynomial is 1. The first Legendre polynomial is x. So we can write the dot product as r1 times r times the first Legendre polynomial of cosine psi, which is simply the cosine. Why are we doing that? Because then what we have is that the last term in the perturbing function becomes r over r1 squared times the first Legendre polynomial, which is identical to the n equal 1 term in the exponential. So the n equal 1 term in the exponential cancels. What we have then is that the perturbation Hamiltonian is gm1, 1 over r1. Now the zero term is r to the r1 0, so just 1, p0. Now the summation is starting from n equal 2. The second term cancels with the last, p0 is 1. And this first term doesn't depend on r, so we can remove it since we're only interested in gradients of the Hamiltonian with respect to r, finding now a somewhat simplified form of the perturbation Hamiltonian. Now we're going to use an approximation that we're only interested in the second order term of r over r1. So we're only going to use the n equal 2 term. What does that mean geometrically? Geometrically, using only the n equal 2 term and ignoring the higher orders of R over R1 implies that you are assuming that R over R1 is a small parameter. So you can ignore the higher order terms. That means R is much, much less than R1. Looking at the geometry of the problem, if R is much, much less than R1, that means that the massless body is much closer to M0. So this is the situation. You have essentially a binary formed by M0 and M2 and an outer perturber, M1, much, much more distant. This situation is called a hierarchical triple. A hierarchical triple is shown here. You have the inner binary, in this case here, label the bodies M1 and M2, and a distant perturber. As long as you can assume that the distance Rn here of the inner binary is much smaller than the distance to the outer perturber, this approximation applies. The approximation of ignoring the higher terms on Rn over Rout applies, and you can keep only the second order term. I emphasize again that we didn't do yet any approximation on what the relative mass of M0 and M1 is. I've been calling M0 the sun and M1 a planet, but there has been no restriction yet on what their masses are. The only approximation that I did so far was to assume that the mass M2 is equal to 0. And that is not that strong an approximation as one may think, because remember that you can always reduce the two-body problem to a reduced mass, where two bodies of non-zero mass are orbiting their common center of mass, and it's proven that this is equivalent to a central body of reduced mass and a massless particle orbiting it. So even if M2 had mass, you could reduce the inner binary to a reduced mass problem and still apply this perturbation theory that we are using. So when is that seen in nature? In many cases. If you have M0 being the sun and M2 being an asteroid, M1 could be Jupiter and you could be solving for this perturbation. M0 could be the Earth, M2 could be a satellite around the Earth, and M1 could be the moon. This would still apply. M0 could be a star, M2 could be an exoplanet, and M1 could be a distant perturber in the same system. M1 could be the sun, M0 could be a planet, and M2 could be a satellite. There are many applications of a hierarchical triple that one can think of. It's a very common situation in nature.